yeah, he said he was going to be with it. So he's not around Loga as in the mathematics class with us. Okay, very good. So let's continue. So just to remind you, last time we worked out the mathematics of Kalun's line reduction, and so we're moving to a study strings on compact spaces. So we worked out so as a warm up, we worked out the study field theory, which is ordinary gravity, Einstein gravity on a Kalun's line space, and we discussed how the action, Einstein did it on action, reduced on a circle. You got a redefined digiton, a redefined Einstein field. You got an extra scalar corresponding to the size of the circle, and you got a gauge field corresponding to G mu 9. Okay, and we worked out the action for that. That's it. We also discussed how objects that carry charge, that carry momentum in the extra direction, are charged under this gauge field. And we discussed how the B mu field decomposes into a gauge field and a lower dimensional B mu field. There's an exercise I asked you guys to do, which all of you have done. Okay, now we're going to move to the study of string theory. And we discussed also that the gauge field that came from the dimensional reduction of the B mu field, namely B mu 9, was different in field theory from the gauge field that came from the graviton, in the sense that there were obvious modes that were charged under the gauge field that came from the graviton, even carried momentum in the extra direction. Whereas there was no, in field theory, there were no modes that were charged under the gauge field that came from B mu 9, and we promised that this would change when we looked at string theory. Okay, so now we're going to start studying string theory with an extra compact circle. First one, and then we'll eventually look at main compact circles. Okay, so let's say that we do x25, but we'll soon drop this subscript just because it's too troublesome. So whenever I write x, we need to drop it. I mean x25s, and we have x is equal to x plus 25. Okay, now. This object is a field, whereas 2 pi r is a number. Okay? So what does this identification mean? It means that the field x is identified with the field x plus 2 pi r. So doing a mode expansion, this identification affects only the zero mode of x. Okay? So this immediately tells us that, you see, all analysis of conformal invariance and so on is local on the worldsheet. Local to the worldsheet, local in space-time. Okay? So nothing is going to be affected. All local properties of the OPs and so on are not going to be affected by one. Okay? However, so this continues to be a conformal field theory. So some identification of an old conformal field theory. This is going to be a good background for a string to propagate. Okay? All that's going to be affected is the zero mode. So we're not going to work out everything that we got from the oscillators again, we're just going to focus on the zeros. So let's do that. So, how does the zero mode go? So, what is the action? The action is 1 over 4 pi alpha prime del alpha x the same. Now, if we substitute in just zero mode here, we got something very simple. We got the integral over 2 pi goes away, and we got 2 alpha prime. Integral x dot okay, let's get the point. Okay, so what we're going to do is to substitute in the zero mode here. Now let's work this out from 2 different points of view. The first point of view is that we worked out from 2 different points of view eventually. But let's think of this object. What's different in the zero mode sector? The thing that's different in the zero mode sector is that a string, okay, with this x being compactified, as you go around the sigma circle. So what we're trying to do is first work out our spectrum analysis. Imagine we're doing a lot like cone quantization once again, like the first few lectures of our course. We're working on a cylinder on the worksheet and we're trying to work on the spectrum. Okay, so what's different? The thing that's different in the xenomorph sector here is that as we go around the sigma circle, it's not necessary for x to be periodic. So what we've done is taken x previously and expanded it as x 0 is a function of time plus sum over I n sum over n by n sigma times sum out by n, and then proceeded to quantize. Okay, this cycle expansion works with this periodicity, but it's too restrictive. It's not necessary for x to come back to itself as you go around the sigma circle, which is the boundary condition we proposed in this expansion. All that's necessary is that x come back to itself up to a multiple of 2 pi r. Okay? So the most general expansion will be this plus 2 plus m sigma r. Okay? X of sigma and tau will be equal to m sigma r. Okay? For some reason. Okay? So let's call this x. M sigma tau will be m sigma r plus x0 is a function of time plus tau. Is this clear? This m sigma r is taken because sigma goes from sigma to 2 pi. This quantity changes from x, wherever it was, to 2 pi r times n, which is the allowed periodicity. Okay? So the field space that we're working with splits up into different sectors, labeled by winding number n. This winding number tells us how many times the Taulic space field wraps as it goes around the worldsheet center.
This is only for the closed strings?
Yeah. Yes, only for closed strings. It's very different from closed strings. We'll return to closed strings. So sorry, I should set that by leaving closed strings. This is the analog of this will be deeper in closed strings. We'll return to that. Okay. So we've got this kind of expansion into sectors. Field splits into smaller sectors. In each sector, we do such an expansion. Okay. So the quantization of this part is unaffected, and is independent of which sector it is. So in each sector, we have a bunch of harmonic oscillators whose frequency goes from 1 to infinity, both for the left movers and for the right movers. Okay? So all we need to, so let's forget about this one and worry just about this part. Okay. So when we do the quantization of this system, what changes? So once again, fine. So there are two things that change. The first thing is that when we plug this kind of configuration into this action, we get a contribution in the action. And more importantly, a contribution in L0 and L0 bar from the two space derivatives sitting this way. Okay? We'll see that more clearly as we go. The second thing that's more important for our current purposes is that the quantization of this x0 thing, which is just a quantization of 1 over 2 alpha prime x0 dot squared, quantization of this action, looks like it's not changed. But that's not true. Because all wave functions have to be periodic until x0 goes to x0 plus 2 pi r. Okay? So, the quantization of this is a free particle moving on a circle, which effectively just quantizes the momentum in the x25 direction. So, the momentum in the x25 direction, p25, is restricted to be equal to n by r. Okay? a solution of this x field in the mth sector. So the mth sector xm of tau sigma, we've got this new piece upon that which is m sigma. That's R. And then we have the old piece which was, if you remember, alpha prime times p times tau. Okay? Why is the alpha prime here, somebody? What fixes the fact that if we want momentum, this thing to be identified with momentum in alpha prime? You have the correct combination. Exactly. So the canonical momentum corresponding to x0 is 1 over alpha prime times x0 dot.
You can also dimensionally argue.
Yeah, you can't dimensionally argue that it's alpha prime or alpha prime times alpha prime. Okay. The canonical momentum is x0 dot divided by alpha prime. Apply x0 dot here, we get alpha prime dot p. Divide by alpha prime, you get by p. Okay? Fine. But we know that this p is n by r. So, in the expansion of the field, we get m sigma r plus n by r alpha prime times tau. And plus the oscillators, which are unchanged, bet what we have. Okay, now let's rewrite this whole thing. It will be useful to rewrite this whole thing. It will be useful to rewrite this whole thing in terms of sigma plus and sigma minus. So let's remind ourselves that sigma plus is equal to tau plus sigma, sigma minus is equal to tau minus sigma. So tau is equal to sigma plus sigma minus by 2. Sigma is equal to sigma plus minus sigma minus by 2. So let's plot that in here. So we get sigma plus into, so we get this x is equal to sigma plus into, well from here we get n by r alpha prime. We get n by r alpha prime. And the whole by 2 n by r alpha prime. So that's, maybe it's a good idea to put an alpha prime by 2. Okay, so n by r plus m r alpha plus alpha prime by 2 into sigma minus into n by r minus m.
The second term alpha prime should be in the term differential. The term containing m doesn't have any alpha.
Term containing m has no alpha. Oh, you're right. Sorry. So, thank you. Okay. Now this quantity here, this quantity that appears behind sigma plus with an alpha prime by 2 taken out, okay, we give it a name. We call it PL. Oh, let's call it PL. PL. And we define PR is equal to n by r minus mr. Okay. Had there been no winding at m with 0, then PL and PR would both have been equal to the momentum. Just n by r. Okay? But then the quantities that play the role of momentum multiplied by the left moving coordinate in the string. Okay? And or the right moving coordinate in the string. So you see, when x had been a periodic field, then the whole expansion of x in the left, the separation of x into left movers and right movers worked for oscillators, but not for the zero.
the zero mode, if we try to make such an expansion, as we did at some point in our course, the coefficient of this would have been p, and the coefficient of that would have been p. So for the zero modes, left movers and right movers were linked, in the sense that their coefficients were forced to be the same. Now we're seeing some sort of relaxation of this link. The left moving momentum, that is the left moving contribution to the zero mode, and the right moving contribution to the zero mode need not be the same. And in fact, in the nth sector, are not the same.
The left moving contribution to the momentum will be
Left moving contribution to the momentum will be
half of
well,
the total momentum is PL plus PR. The total momentum is N by R.
the total momentum is n by r, Pn reduces to n by r, if n is equal to 0. So you take all the halves out, such that Pl would have been the ordinary momentum, had winding been 0. Similarly, PR would have, we accounted for the normalization of wave. I mean, manifestly, that's why I took this alpha prime by 2 point, to get an object that would have reduced to momentum otherwise.
So if you want to think of it physically as the momentum carried by the left moving
You see, it's not quite, well, as the momentum carried by the left moving.
for example, if I write down the mass formula,
Right.
then it
We'll do that just now. It's a PL, you see, in the mass formula, PL will appear exactly like P appeared before. Because much reduced to the whole mass formula will appear. Okay? So fine. So at the formal level, what we're doing, physically is clear. We're adding windings. But you see something interesting happening at the formal level. At the formal level, it's making the zero modes behave more like the oscillators. In the sense that we're allowing what's happening on the zero mode side of the left movers and the zero mode side of the right movers to become different. We're allowing ourselves to become different, for these two things to be different, the left and right. Is this clear? Okay, now let's immediately write down the flow pattern was asked about. And read the dispersion relation, the formula for the mass squared of particles that arise in this compact relation. Okay, so now to do that we want to know what L0 is. So L0 as before gets contribution only from PLs, and with the normalizations that would have said equal to P, had PL is equal to P. So L0 is equal to alpha prime by 4, it's the usual one, PL squared plus alpha prime by 4P squared. Okay, so this is, now the rest is in the non-compact direction, this is what we call the mass squared. It's minus alpha prime by 4 mass squared. Minus because space-like momentum contributes negative to mass. Right? And then plus NL minus 1. NL is the naive oscillator number, and the minus 1 comes to the energy of the transient, cascade energy of the transient. Okay? And L0 bar is equal to minus alpha prime by 4 PR squared minus alpha prime by 4 M squared plus NR. No, sorry. This is mass. I'm sorry. This end is a winding number, it has nothing to do with this. This is mass, that's called. You understand? Look, suppose we've got a mode. Okay? It carries some momentum in the non-compact directions.
only this
I see. This mass square is k square minus mass square is k squared in the non-compact directions.
Okay.
Right? Which we equate to mass square because we get a Schrodinger type equation with this value of the mass.
So are we thinking of it as an extra compact dimension or okay, this is the mass if we are dimensionally reduced.
This is the mass if we are dimensionally reduced. You see, mass is a well-defined notion when we've got a Poincare algebra. And we've got no Poincare algebra in the direction in which we dimensionally reduced.
Okay.
So we're looking at the mass square of the effective particle in 25 dimensions. Okay? So by mass square, I just mean k is minus of k square in the non-compact dimensions. Is this clear? Okay? So we get the formula mass square is equal to PL square plus 4 by alpha prime into NL minus 1 and also equal to PR square plus 4 by alpha prime into NR. Now, when we were dealing with the x coordinate that had no identification, PR is equal to PR, and the equality of these two told us that NL is equal to NR. Now, PL is not necessarily equal to PR, and NL needn't be equal to NR. What once we do is that these two quantities are the same. Okay? But it need that in general will not imply that NL and NR are the same. Okay, so
so there is some complicated relationship between m and n here because nl minus nr will be an integer, right? If we just subtract.
Yes. So we will not be able to satisfy the mass strength condition for arbitrary mn. You know, so for crazy values of the radius, okay, we will not have physical particles yeah. So Logarithm's point is that if we subtract these two, so let's do that. So Logarithm's point is that if we subtract these two, what will we get? Okay, so what we get here is PL squared minus PR squared, which is equal to 4 times mn by alpha. Okay? And that must be equated with nr minus nl 4 by alpha. Okay. So, the equivalent of the level matching condition for cancer is that nr minus nl is m times n. So you fix a value of n, then you must satisfy this condition. You must choose your oscillator excitations. That's the way to think of it. Fix some n, then you have to choose your oscillator excitation from the right and the left such that this difference is made.
We still have transmission and invariance in this circuit.
We have translation.
Is this the statement of that?
I didn't understand. What do you mean?
I mean, so we should get some condition out of that. Imposing
Some condition on
condition on
this charge here, this n by r is the momentum corresponding to translation invariance. I have understood. This is just a level matching condition on the string. The fact that L0 has to be equal to L0 bar. Okay, applied to this system. And it reduces, in the case that n is equal to 0, to the condition that nr is equal to n. But it's different from the condition n r is equal to nl and non-zero nl. So notice that you always get an integer. So it's a fulfillable condition. It's not something that depends on r or depends on alpha primes. Given any m and n, there are always values of nr and nl that satisfy this condition. Is this clear? Okay, good. Let's go. Now, I want to look at this mass squared formula in a little more detail. Okay? So, let me look at this. Okay. Okay. Before going into the detailed analysis that I'm going to go into in a moment, notice one thing immediately. This PL, both PL squared and PR squared have a certain invariance property, a certain formal invariance property. So suppose I do the following. Suppose I take R and set it to alpha prime divided by R. Okay? And so, and I said M is equal to n prime and n is equal to m prime. Then Pn as a function of R, M and n is equal to Pl as a function of R prime, M prime and n prime. Whereas PR as a function of R, M and n is equal to minus PR as a function of R prime, M prime. Can you see this? You see, I exchange R by alpha prime by R. So I get alpha prime times R prime, yeah? And I exchange n by n. So this term becomes that term, and vice versa. Similarly, these two terms get flipped. And because of the minus sign here, we pick up this minus. Okay. So, what does this say? This already tells us something very interesting. Okay. It tells us that a string on a circle of radius r has exactly the same spectrum as a string on the circle of radius alpha prime. The spectrum is the same, but in order to map states to each other, you need to flip labels. This flipping of labels is m is equal to n prime and n is equal to n. Now, this from the point of view of quantum field theory, from the point of view of just gravity of a circle, seems very non-intuitive. You see, because we just have gravity in a circle, you've got a bunch of massive modes coming from the Kaluza-Klein states. And these states are more and more massive if the circle gets smaller and smaller. Certainly, it's not true that a small circle and a big circle have the same spectrum. So what's going on? You see, what's going on is that in string theory, in addition to the Kaluza-Klein states, you have states that wrap the string, the winding states. Now, just as the Kaluza-Klein modes get heavier and heavier as the circle goes smaller and smaller, the winding states go lighter and lighter as the circle goes smaller and smaller. So, the heavy Kaluza-Klein states of a small circle turn out to have exactly the same mass as the heavy winding states of a big circle if we change R to alpha prime. And vice versa. Okay? So you see something very interesting. If you're looking at physics from the point of view of a low energy observer, you cannot, at least at the level of spectrum, you shouldn't see that this is a more general thing than just a spectrum. You cannot distinguish between string theory compactified in a circle of size R and string theory compactified in a circle of size alpha prime pi. The spectrums are identical. And the way it works is that the winding states in one picture, that's the momentum states in that picture. And vice versa. Winding and momentum quantum numbers are interchanged. Okay? We've only seen the subpart level spectrum. We'll soon, either at the end of this lecture or the next lecture, understand this is a full non-perturbable symmetry of string theory. Okay? This is our first glimpse at the symmetry of string theory called T-duality. Okay? Now, just a little word, we're going to go on with our technical analysis in a moment, but just a little word about T-duality. T-duality hints at something. It's just a hint because it's just a hint. But it hints at a phenomenon that we will see again and again in string theory. That in string theory, it's hard to go beyond the minimum length scale in some sense of thinking. You see, you might have thought that you were sort of looking at a compactification that dealt with very small length scales, like compactifying a very small circle. But it turns out you get exactly the same spectrum as if you compactified in a large circle. Okay? So, in string, in a more fundamental way, we would say that there is no way to distinguish a string compactification on a very small circle from a very large circle. There's no way to distinguish string compactification on a circle of size R from string compactification on a circle of size alpha prime. So the very notion of whether something is big or small, once you get down to string lengths, at least as far as the size of the circle is concerned, seems to become ambiguous. Okay? And this is one of the first indications, and we'll see many of these as we go along, that somehow the notion of space and time must get modified in string theory. The absoluteness of big and small must get modified in string theory. How that plays out in the end has not yet been worked out properly. We don't understand exactly what replaces these notions. But we have many hints that this notion must get replaced. Yes?
Is this true even if we slightly deform the circle?
Is this true if we slightly deform in what way? Meaning?
Let's say no more circle.
You see, you can have to do it in a way that solves the equations of motion. Okay? So now, in many situations, there are generalizations of this to. So, let's look at string theory compactified in a Calabi or math. Some complicated compactification. There are analogous phenomena to this. Okay, these phenomena are called mirrors. Okay, we'll discuss much of these things as okay.
Is there a reason why you would expect that this to be true about arbitrary?
No, one shouldn't take this too far. It's not a claim that, maybe basically the point is, basically at the level that we're talking about. The main point is that, there are winding modes and there are momentum modes. And you can interchange the two. Okay. As long as this statement continues to be true, at some intuitive level, you'll have a hard time distinguishing between big circle with winding and small circle with momentum.
Okay. Can you just rephrase this?
Please.
Let's say I take some bunch of strings.
Yes.
So it will definitely have some gravitational effect, right? Because there's a gravity in the field.
Yes.
And this circle will react to that.
This circle will react to that. Yes.
Because it's a part of the space.
Yes.
Now, so in what sense are we saying that we can't distinguish between the two? In the sense that, if you give me a small circle and if you give me a big circle, can I by slightly deforming the circles make out whether it's a big circle?
What do you mean by slightly deforming?
By using by string probes themselves, because
you see, anything that can be built as a small deformation out of this cannot be distinguished, because any experiment you perform in one picture has the yes, okay, what is true is that, suppose you've got a massive state. Okay? If you can prepare a probe that you know is winding to it, then you can check whether that state is winding or moving. So, if you have some way of saying this is winding and that is momentum, then you can distinguish between these two pictures. Okay? But for any experiment you can perform in one picture, there is a corresponding experiment you can able to perform in the other picture with different probes, but which will get the same result.
I mean, there is obviously my probes don't deform this level, but I mean, is it evident even if the probes?
You see, conformal field theories here are just the same. Okay? So, to the extent that string perturbation theory is determined completely by the world sheet conformal field theory, these two things are the same string compactification. You see, any question you have in one picture has a corresponding, any experiment you set up in one picture, has a corresponding experiment you set up in the other picture, that will give you the same answer. You see, both momentum states and winding states live all over the circle. Both of them carry gravitation. Now, it's not obvious that you can distinguish in some invariant way, and it's to the extent the string perturbation theory of at least. It's not true. There's nothing you can do as a small perturbation around this picture to distinguish between these two. We haven't shown that, but I will show you that these are just identical as conformal field theories. And string perturbation theory is determined by the conformal field theory of the world sheet of strings. Two things are identical. Conformal field theories, they're just identical. It is identical perturbation.
I'm just worried that this statement that they're identical seem to depend on the fact that this thing is a circle. I mean, both of them are circles.
So, but if you can take something and think of it as a small deformation around this,
Okay.
it's a small deformation in one picture or the other.
So any small deformation here you're saying can be mapped out. So
It can be written in either picture.
because any small deformation is just some amount of
Some vertex operator put on this thing, and this, if it's one, you put this vertex operator in one picture, it's another. It's the mapped vertex operator in the other picture.
So if I start here and start deforming,
Right.
using vertex operators,
Right.
then at least to the extent that the string perturbation theory is valid,
Yes. Yes.
I mean, this I mean,
You will not be able to distinguish this from starting with the other picture, putting on the corresponding deformation, and doing the corresponding experiment. Okay. We're going to get back either at the end of this lecture or later in the next lecture to a more detailed study of T-duality. It will be useful to have the vertex operators corresponding to these states. At this point, it was just to whet your appetite. So let's now go back to the analysis of the spectrum. Okay, and let me start by analyzing the spectrum. First, as in our study of non-compact string theory, a particularly interesting question is what are the master states over there? Let's first do this with an arbitrary value of a radius, and then specialize the special radii. Okay, a radius that will turn out to be particularly interesting is the radius at which under this operation, r does not change. Namely, r is equal to square root of r. Okay? That will help us in understanding. But let's first just do this at arbitrary space. Okay. So suppose we want to understand what the massless particles in the theory are. Okay? We want to understand what the massless particles in the theory are at some arbitrary. Now, because R enters in a complicated fashion in this expression, if we're in an arbitrary radius, the only way to, generically, the only way to satisfy this relationship is to have this equal 0. back to the old analysis again. So we have NL equals 1, NR equals 1 at R. Okay? And so what are the modes? What are the states? The states are alpha minus 1, alpha tilde minus 1, Mn acting on 0. But remember, these Mn's could be either 25 or mu. So now there are many options from the point of view of the lower dimension here. Firstly, if Mn equals mu, what we recover is the dilaton, the graviton, the B mu nu field of the lower dimension. If M and N are both run from 1 to n. However, if one of M and N is mu and the other one is 25, okay, what do we then recover? So then let's, for instance, suppose we have alpha minus 1, 25, alpha tilde minus 1 mu. This has a single space-time index, so it's a gauge field. Okay? So we recover a master's gauge field. There's a second master's gauge field, which is minus 1 mu alpha tilde. In fact, actually, it's the symmetric and anti-symmetric combinations of these that are most natural. Okay? And these two master's gauge fields are what we saw in our analysis of Kaluza-Klein compactification last class. Namely, the master's gauge field that came from having one leg of the graviton in the 25 direction and one leg of B mu in the 25 direction. Okay? And finally, there's a case where we have alpha minus 125, alpha tilde minus 125, and 0. And this is a scalar from the point of view of the remaining non-compact dimensions, and it's the additional scalar that corresponded to the size of the circle. Remember, we had in addition to the low dimensional dilaton an extra scalar to the size of the circle.
How do you identify which one among the gauge fields?
Among the gauge fields, you see, from the point of view of field theory, one of the gauge fields came from dimensional reduction of the graviton. The graviton is a symmetric combination. Whereas the other one came from the dimensional reduction of B mu, and B mu is pan-symmetric. Okay? Good. So, add arbitrary values of the radius, we've recovered what we saw last time from field. Okay. There's just one little point I want to make. There's one little point I want to make here. Okay. Okay, which goes as follows. Let's look at the vertex operator corresponding to the gauge field that came from B mu. Okay? So alpha minus 1 maps to del x. Alpha tilde minus 1 maps to del bar x. So the vertex operator will be of the form del x25 del bar x mu times minus del x mu del bar x2 times e to the power I k dot x. Well, in this case, purely in the non-compact dimensions. Okay? So this is going to be the vertex operator that corresponds to the gauge field that came from the dimensional reduction of B mu. Now, if you're interested in measuring the charge, okay, the net charge of the system, you couple, the derivative of a Lagrangian with respect to A mu gives you the gauge field. Okay, A mu at x gives you, the current at x. And if you're interested in J mu integrated over all space, you take the derivative with respect to the zero mode of A in momentum space. So we're interested in measuring net charge under the gauge field that comes from the coupling B mu. We should be interested in this vertex operator at k equals 0. Okay. Now, at k equals 0, that's what this vertex operator is. And it's very near to being trivial. It's very near to being trivial, as you can see in the following way. You see, this thing we can write as, using the equation of motion of, exactly, let's take a del out. x25 del bar, okay, this, I've subtracted an extra term here, which is del bar x2, which is 0. Okay, and then we could also write this term here as minus, for instance, del bar of x25 del x. We could do it many ways. Right. But what I want you to notice is that each of these terms here is a total derivative. Okay? So this object, if we were working on a compact world sheet, and if this quantity was single valued, okay, then insertion of such a quantity onto the world sheet would give you something trivial. It would just give you something that's 0 by the equations of motion. For instance, if this was the integrated vertex operator and calculating some correlation function. Okay? So, if the other operators that we insert into the worldsheet, onto the worldsheet, don't create are such that this vertex operator, the path integral in the presence of those vertex operators, all these single valued fields, then we just get 0. On the other hand, x25 need not be single valued. The other vertex operators that you put into your worldsheet going to force x25 to wind around. And then this vertex operator is not trivial. Okay? So what we are seeing is the fact that only states that have winding number in x25 can carry charge under the gauge field that comes from B. Now, in fact, the states that have winding number under x25 do carry charge under the gauge field that comes from B medium. And to convince yourself of that, I'd like to suggest a little calculation. Okay? I want you to calculate the 3-point function, 3-point scattering of the gauge field now with some momentum. Of the gauge field that comes from B mu with some momentum, and 2 tachyon operators which have equal amounts of momentum. Okay? Now,
can't we just argue from this?
Yeah, you could. Basically, what you're going to get is
because the charge under the gravity, the mu from gravity is basically n.
right.
So, if the interchange have to work out, then the charge under that mu should be n.
That's absolutely right. That's absolutely right. And yeah, as we will see, the stereoanity symmetry is a symmetry under which xl goes to is equal to xl, whereas xr goes to minus xr. In 25. And under the symmetry, momentum gets interchanged with winding, the gauge field from B mu gets interchanged with gauge field from algebra. So that follows from all of that. But nonetheless, I would like you guys just to do this calculation explicitly. Okay? So what calculation there is to do is clear, right? You know what the vertex operators are here. Actually, I haven't quite told you about the vertex operators for states that carry winding. Sorry, this has gone in slightly order. I'm going to tell you about that in a moment. Once I told you about that, you know what vertex operators to insert. Okay? And you know what the vertex operator for this B field, for this B gauge field is that we've written down. Yeah? Then it's a simple generalization of the many calculations we did before for 3-point functions in the closure set. Okay, but I'd like you to do the calculation just to get your hands wet on this stuff and to check that you will find it coupling only with states that have non-zero winding. Okay. as Logan says, there are many more structural and sort of general ways of understanding this. Okay, good. Why did I bring this up at the moment? I brought it up because already at the left at an arbitrary radius, we see one phenomenon in string theory that we did not see in field theory. Namely, the gauge field that comes from this BB mu carries states that have charge. Okay? And these states are bounded on the extra. Okay. So, as an arbitrary value of the radius, if we are interested only in this massless spectrum, that's it. There's nothing else.
But all these states are really
Which other state?
I mean, the states that start in the
An arbitrary values of the radius constraint. Okay? Not an every value of the radius as
yeah.
Okay? However, now you just to answer the kind of question don't have. Okay? Let's focus on a particularly interesting value of the radius. The particularly interesting value of the radius that we focus on is r is equal to square root alpha. This is the self-dual point and the r goes to alpha prime alpha. Okay? It's the point in which there are two different descriptions of the same theory, without changing the radius. Okay? And let's examine the spectrum here as a warm-up to understanding the physics of it. So I'm interested in the mass of the spectrum. So we have that n squared was equal to n by r plus w r by alpha prime. Yeah, the whole thing squared plus nl minus 1. It was also equal to n by r plus w minus w r by alpha prime plus n r. This was true in general. Now if we said r equals square root alpha prime, what happens? What happens is that was a 4 by alpha prime. Okay? What happens is that we get each of these things has is proportional to 1 over square root alpha prime. So we get m squared is equal to 4 by alpha prime into n plus w, the whole thing squared by 4 plus nl minus 1 is equal to 4 by alpha prime into n minus w, the whole thing squared by 4 plus nr minus 1. As the special value of the radius. Okay? And now let's search for solutions to the problem of masslessness. Okay. So let's start. See. We have to cancel this minus 1. We can do it either with NL or with this N plus W. So let's see how we can do it with N plus W. Okay? So I'm going to write NW in a bracket like this to denote the quantum numbers of the state time. So one way we can do it is if we choose NW to be 2, 0. You see, in order to cancel minus 1, this minus 1, we need N plus W to be equal to 2. So one way to do this is to choose NW to be 2, 0. That way, NL and NR both equal 0 will satisfy this equation. And give you a massless particle. You see? Because this will give you 2 squared, so that's 1 minus 1 plus 0. we've done this, there are clearly three other solutions to this function. There's minus 2, 0. Let's put this in the bracket. 0, 2, and 0. Each of them with NL is equal to NR2. Okay? And that's it for massless particles with both NL and NR equals.
This is clear.
Okay? Okay? But this is of course not the only way to get massless particles. We could also try N and W are 1 and 1. That will also sum these two. So we could try 1, 1. And then if 1, 1 works, minus 1, minus 1 also works. Okay? Then we said NL equals 0. But now NR is not equal to 0 because 1 minus 1 is 0. So we have to set NR to 1. Or we could try 1 minus 1 and then minus that works. NL equals 1 and NR equals 1. And then finally there's 0, 0 with NL equals 1 enough. This is a comprehensive list of the ways in which you can get massless particles at the special value of the radius. Okay, it's now an interesting exercise to take these massless particles and to group them in with symmetric properties under the Lorentz group of the non-compact directions. Okay, let's first count, group together the scalars. Count how many scalars. Okay, scalars. You see, each of these cases, there are 4 scalars here, that's clear. Okay? Now, whenever NR is equal to 1, the index will either be 25 or mu. So choosing 25 will get a scalar. So each of these options has the option of putting all of these guys 25, anything that's not equal. So each of these also gives us a scalar. Okay? So we've got 4 plus 2 plus 2 plus 1, so 9 scalars. What about gauge bosons? And gauge bosons are objects with a vector index free. Okay? So we get nothing from here. 2 from here. 2 from here. And 2 from here. Because one of these could be 25, the other one mu. And which one there's not? 6 here. Okay? And finally, what about higher dimensional things, like the tensors and so on? Well, that's exactly what we had before. This 9 scalars. Yeah. So that's not counting like a trace of. There's also the idea where you had mu. The trace part of alpha mu. So that's the dilettone of the lower dimensional case. That we're not counting. 9 scalars plus the dilettone of the lower dimension. Okay. So, everything the field theory would the boys. That is D mu nu, and phi to the edge. Now, these three here are interesting. These gauge bosons, these 6 gauge bosons here are interesting. You see, 2 of these gauge bosons came from here. Came from taking a mu index here and a 25 index here. These were familiar. These are the gauge bosons that come from dimensionally reducing the graviton as the beam. But what about the other 4? Those came from here. Had no contribution from non-winding sectors. All of these have W not equal to 0. And so purely stringy objects. There's no field theory. There's no gravity. It's purely gravity. Okay? Now, I'm soon going to show you, as once we study the vertex operators corresponding to these guys in a little more detail, I'm soon going to show you that these 6 gauge bosons group together into an SU2 times SU2 gauge boson. These are not 6 UR gauge bosons. They are in fact gauge bosons of a non-abelian gauge group. You can see this immediately actually. You see, all of these guys carry momentum and winding, and therefore are charged under the gauge boson that comes from dimensionally reducing the graviton and dimensionally reducing beam. Okay? So this is the theory of gauge bosons such that gauge bosons are charged, carry charge under other gauge bosons. The only consistent way to do that is in a non-abelian gauge.
It's also clear that this is like W plus W minus.
Exactly. It's like W plus W minus A and W plus W minus. And I will also show you that these 9 scalars transform in the fundamental bifundamental of this SU2 times SU2. Okay, so these guys also carry charge under momentum and winding, these scalars. So they also charge under this SU2 times SU2, and we'll examine in what way that happens. So now I've not shown you all of this, but we're already beginning to glimpse very interesting things. You see, what do we see? We see that you take string theory, which when non-compact was relatively boring, in the sense that the fields had no non-abelian structure. Okay? There was a graviton. Listen.
So these 9 scalars are in the fundamental
In the fundamental bifundamental. You see, you have to say how they're charged under each of the 2 SU2s. So there will be like this 5 IG bar. Fundamental argument. Sorry, fundamental argument. So of this SU2. It's not even fundamental. It's like 3 times 3. It's in the 3 times 3. Right. But these I and J are SO3 vector indices.
You can understand that W plus W minus analogy. I mean, okay, fine. These the 4 actional neighborhoods that we are seeing here does carry momentum and winding, and therefore would be charged under the
And they get plus 1 and minus 1.
So for every plus, there's a minus. Yeah. Hang on for a little bit. We'll see this all in much more detail. Okay. So, fine. So, we're going to see this in more detail, as I'm promising. But even before that, I wanted you to see how interesting this is. You take string theory, and you put it in a circle. When it's non-compact, you put it in a circle of an arbitrary size. the massless spectrum is just that of U1 theories. You know, the U1 gauge, the two U1 gauge bosons, and it came from something with no non-abelian structure, graviton. Okay. Then you tune this circle size to a particular size, and suddenly you see the emergence of non-abelian symmetry. Okay, we'll see that. You might ask, how does it go away? How, when you move from this particular size to another small size, does it go away? And we'll say that basically will be like a Higgs mechanism. You know, the non-abelian symmetry will be broken to U1 times U1 by an effective Higgs mechanism. We'll see all this as we go along. But you know, it's quite interesting. You get, there's a new source of non-abelian gauge symmetry. This new source involves winding strings inclusion. Okay? There's more symmetry than you would have thought. The same situation, which displays a very small amount of symmetry, maybe U1 times U1, in field theory, actually has a hidden SU2 times SU2 symmetry from the point of view of string theory, which has been Higgs away when you move to large circumstances. Okay? We'll see this all in more detail. Just to give you the lay of the land before we do it.
So the field theory actually based on at some.
Well, there are new massless states. You know, the reason the field theory is a good approximation when every other state in the theory, every other string oscillating state, is well separated from it. That's no longer true. The new massless states. Okay, it will be actually very similar to, you know, looking at an SU2 times SU2 theory with matter in the 3 times 3. And then you slowly turn on a wave to that matter. Okay. At the origin, there's all the non-abelian structure. When you move far away, you just have the U1 times U1. Clearly, the effective U1 times U1 theory breaks down as the wave of this thing goes to 0. Then the W boson and mass become
In that case,
small.
you would see it restored at some high energy scale.
You would see it restored.
I mean, some effective way. I mean, this is that.
Right.
This is not happening.
No, I think you would see it restored at some high energy scale here as well. You see, if you go to energies such that you can ignore the mass difference between these winding states. See, these winding states always exist at every value of the radius. It's just that they're not massless at every value of the radius. If you go to energies such that you can ignore the mass difference between these massive W bosons and the massless two ones, you will see the approximate SU2 symmetry. It will be the same kind of thing.
So this will be some transition which is just a temperature which is around space.
Which, yeah, if you have a generic value of the certain size, which will be announced. That's okay. You have to go to energies in that order before you start saying. Okay. Very good. So, this was to show you how, in the presence of binding, you can get new, interesting low energy physics, new master states, and new phenomena. We're going to come back and discuss all of this in more detail. But in order to do that, it will be helpful to understand the vertex operators of this theory. So let's get to there's a partition function. Sorry, right at the beginning of this lecture, I should have calculated. Okay, I'm sorry. I'm going to take a 10-minute break before we go into vertex operators. This is just to do with spectrum once again. Just to compute at an arbitrary value of the radius the partition function, the one-loop partition function, this theory on the torus, just to show you how modular invariance is recovered. Hitting this. I'm sorry, this lecture has become a little haphazard. I have to go on a linear order. But it will all come together. Okay, so we're rewinding to discuss the partition function of the string theory at an arbitrary value of the radius. Okay, so get from the oscillators is unchanged. Okay? So suppose we've got this X conformity theory, we want to compute its torus partition. So if you remember, we had defined, I'm not even sure I defined this beta function for you. So we want to define it. So there's a part that comes from the oscillators, including 0-point energy. Which is totally unchanged in this level. Okay? So what are we doing? We're computing the torus partition function. We're computing the torus partition function of the part of the conformity theory that comes from this X. It's just this one person. Okay? So we have this term that comes from the oscillators and nothing has changed. So we have this, which by the way mathematicians like to write as eta of tau mod squared. And we can write it as eta of tau mod squared just because it saves us a lot of writing. Okay? So the partition function is this business times what? Times whatever we get from the 0. Okay? So now let's discuss what we get from the 0. In the case of non-compact theory, remember the way we did it. We said that, well, what we have is the spectrum of a particle on a circle of size tau 2. The spectrum of a particle on a circle of size tau 2, and the particle has effective mass 1 over alpha. Okay? And then we said, well, then that is tau e to the power minus tau 2 times k squared plus n squared dk integral. Then we did the Gaussian integral and we got the answer that was proportional to 1 over square root tau 2. Okay? Now we want to do the analog of this here, but there are two differences. Okay? What are the differences? The differences are, firstly, that firstly that we have winding, and secondly that momentum is discrete. Okay? So let's do it more carefully. So what we're going to do is compute the trace of q to the power n0, q bar to the power n0 bar, from the 0 mode sector, from the 0 mode contribution of that, when we have the separate compact. Now, L0 is simply equal to 4 by alpha prime KL squared, the contribution of 0 modes, and L0 bar is 4 by alpha prime KR squared. So what we want to do is to compute trace of, and this trace now is just a sum over n. Q to the power 4 by alpha prime KL squared, Q bar to the power 4 by alpha prime KR squared. Where, remember, KL and KR were what we had before. This is 1 by 2 up, that was alpha. Okay. Now, let's remind ourselves also that this Q is equal to e power 2 pi tau, and Q bar is equal to e power 2 pi tau. And tau is equal to tau 1 plus pi tau. Okay. Now you can take all these definitions, plug in here, and get some expression as an exponential involving m, n, tau 1 and tau 2. Okay? the algebra that I'll take for the problem can be done. I'm just going to go through this. Okay. This thing is exponential of minus pi into alpha prime n squared by r squared plus n squared r squared alpha prime plus 2 pi I tau 1. This thing is equal to this thing. Of course, we still have to sum it, right? By the way, can somebody give me an interpretation of this tau 1 which multiplied by n times w? Does it remind you of something we saw at the beginning of this class? What does tau 1 couple do? Yeah, we just plugged in tau 1 here. The operator multiplies L0 minus L0 bar. L0 minus L0 bar is integral. So the integral over tau 1 in the integral over the moduli space of the worldsheet of the torus will enforce that L0 minus L0 bar of the oscillator L0 minus L0 bar is equal to n times w. That's something we saw before. There's a new contribution couple proportion of tau 1 compared to what we had just on the oscillator. Okay. The usual thing for the non-compact guy was that the integral over tau 1 enforced that L0 is equal to L0. Okay. So this is a sensible thing, and then this is where it is. This is essentially like the energy of the state. Okay. Now, I'm sorry. Polchinski called W, in my notes I have A. I was looking at Polchinski and trying to translate W to M in some place. Thank you. Okay. Now, you see, this expression here is multiplied by this 1 over eta tau, and written this way, it's far from obvious. It's far from obvious this expression gives us a modular invariant one-loop partition function of the torus. There are two sources of non-obvious. But firstly, mod eta squared by itself is not modular. It needs an extra factor of square root of tau 2, exactly. Square root of tau 2 into mod eta squared is mod. Okay? So first we need a factor of that somehow, and then the sum has to be modulated as well, and it's far from clear that that's the case. However, there is an interesting trick here, an interesting technical trick that allows us to demonstrate modular invariance and has a physical interpretation. So let's first look at the technical trick and then look at its physical interpretation. So what I'm going to do is take the sum over n, that is the sum over all the momentum modes along this circle, and do it after and Poisson result. Okay? Let me remind you what that means. Okay. See. Suppose you've got some function, some f of x, which has a Fourier decomposition, which is equal to f of k, f tilde of k, e to the power 2 pi I kx. Okay. Now, I want to claim that the following is true. That the sum, provided there's reasonable follow-up properties of these functions, the sum of f and m is equal to the sum of f tilde the 2 pi z. Okay, now this is something you're all familiar with, but let's quickly see. Oh, can I leave it here to check that this is true, or you know that this is true? Yeah, I mean, you know, basically what's the point? Suppose you take this thing, say, what do you want to do? You want to take this and sum it over all the values of a. So that's what you want to do is to calculate, that's the same thing as integral dk f of k, and then sum over n e to the power 2 pi I k m. Okay? So you want to know what this thing is. Now this thing is a little ill-defined as it stands, but one way to understand it is to put, to discretize space-time and compactify it. Put the values of m to be periodic with periodicity in, to discretize the possible values of x. And then allow k to take the allowed values, namely m divided by n, to respect the periodicity of the problem. Hey, my method is substantially better. Let's just do it. Okay, so suppose we're given a problem in which we have periodicity of this function or as a function of x or with periodicity capital A. Okay, then the allowed values of k, okay, then the allowed values of k would be k is equal to m divided by n. Okay, and of course there would be, because we're only looking at things, at discrete points, there would be an effective periodicity in k. M goes to m plus n would be a periodicity of this function. Okay? So now this is a very well-defined mathematical object. Okay, let's call it R. So suppose we do sum over n. This is e to the power 2 pi I R m divided by n. M runs from 1 to n. This is very clear. Right? This object is 0, sum over the various roots of unity, the nth root of unity. So it's 0 unless R is either 0 or n or 2n and so on. Okay? So this is equal to, and when it's one of those values, it's n times delta R 0 plus delta R n plus 1. Okay? But now you want to undo this discretization to go back to continuum language. So this sum over n becomes like an integral over n. But we're interested in integral over k. And the difference between k and m is the factor of n. Okay? So if we want this to be true, if we want to replace this by an integral, these get replaced by delta functions separated with the factor. Okay? The only tricky part in this whole process is getting that normalization, right? But this is correct. So once you define things this way, this is correct. Okay, great. So now, we're now going to apply this formula. We're now going to apply this formula to that object, with x being taken to be the object n. Okay? So what we want to do is to compute integral e to the power 2 pi I, and now we'll replace n by, let's say, r. So 2 pi I, no, down to multiply. Yeah, we want e to the power 2 pi I r x then minus pi tau 2 alpha prime by r squared x squared plus 2 pi I tau 1 into xm. Sorry, xm. Right? There's also this part. But since that does not involve our variable n, which I call x, okay? It just goes along to the right. So let's do this stuff. Let's do this integral. Firstly, you see this part and this part are very similar. So this is integral e to the power 2 pi I, and then there is r plus tau 1 times m times x, and then minus pi tau 2 alpha prime x squared by x. So what do we get? We get in doing this integral, we get the factor of square root pi that we get from a Gaussian integral. Then we get square root of this stuff. So we get square root pi, square root alpha prime r, and then a square root of tau 2. And then we get what we get by completing the square. That is the exponential of, so completing the square, we remove this 2, we take this and square it, pi squared, r plus tau 1 m the whole thing squared, and divide by whatever's here. So pi tau 2 alpha prime and r squared. Where's the half? This 2 just cancel the fact that it's twice. If you complete a square,
So the standard deviation, the variance gets inverted. So it should be 2 sigma squared.
You want a 2 here.
So I think there should be a factor of 4. So it gets inverted.
Very good, very good, very good. I hope that's not really going to be trouble. Wait a minute, all I've done is complete a square. Okay. And I've completed, so this thing, no, I think this is okay. You see, what I've done is,
Okay, fine. Okay, you left out the 2 when you square it, right?
yeah.
This is the 4.
Yeah. Okay, so this is r by square root alpha prime tau 2. No, it's the 1 by tau 2. This is the thing that we wanted to take the module and there is beta. Times the exponential. And now so pi cancels this. We have, and now we added what we had from here. And there's minus sign here because the I square. So minus pi minus pi into tau 2 m squared r squared by alpha prime plus r plus tau 1 m the whole thing squared. But that's an r squared as well. At about alpha prime. Alpha prime. Right, I got all the r's that's one right. This had an r square, that had an r square, so that's good. Yeah. And when you put some tau 2 somewhere, here there's a tau 2 there, and here there's a time. Let me make this tau 2 squared divided by tau 2. Okay. And now, this numerator can be written as exactly. So we've got r divided by alpha prime square root tau 2 exponential of minus pi r squared by alpha prime mod of r plus m tau square divided by tau. Okay, and this is summed over all values for r and m. Now this is a much neater form from the point of view of modular invariance than what we had before. For instance, there was no hope to modular invariance in the original thing. There were all these factors of r that appear differently in different terms. Now all the r factors have come out, so there's no hope this is simply modular invariant. And let's check. Under tau goes to tau plus 1, that's obviously modular invariant. Under the redefinition, n goes to n minus 1. So r goes to r minus 1.
R goes to minus 1.
R minus n, thank you. Thank you, right. So under tau goes to tau plus 1, this is obviously modular invariant. What about tau goes to minus 1 then? Okay? Now tau goes to minus 1 by tau. Yeah, let me look it up here. Let me check it. M goes, his M. He has, his M is our R. His R goes to minus M. And M goes to R. This is modular invariant under that transformation. We can check. Can I give you to check? Oh, yeah. Okay. So, okay. So tau prime is equal to minus 1 by tau. Okay. So what's the imaginary part of this? So this is equal to minus 1 by tau bar into tau bar. So im tau prime is equal to im tau divided by mod tau. Okay? Now put the same kind of thing, right? Okay, it's a simple thing to check. Okay, right. So this thing is modular invariant. That's correct.